Thank you. Thanks everyone for coming. Thanks, thanks to the program committee for inviting me to give this talk, and thanks to the local organizers for this wonderful conference. All right, so I'm going to be talking about an exponential quantum speedup for solving a classical problem. It's going to be a classical problem about simulating coupled classical oscillators. If you don't know what that is, that's okay. I also did not know what that was before we started this project, and I'm not really going to explain what that is. So I'm just going to take a specific example of a coupled classical oscillator system for this talk. This talk is joint work with Ryan Babish and Rolando Soma, who are at Google Quantum AI with me, Dominic Berry and Nathan Weeb, who are at Macquarie and University of Toronto, respectively. Okay, cool. So let's start with a quick summary of what this talk is going to be about. If this pointer works for me, yes. Okay, good. Right, quick summary of what the talk is going to be about. So the first thing, we define a new computational problem that's related to the simulation of this classical system that I was talking about. For this talk, I'm just going to talk about a classical system of balls and springs. So the problem is just going to be about simulating the time evolution of a classical system of balls and springs. Okay, so we take this new problem. We show that this problem is in BQP. In other words, it can be solved by a quantum computer in polynomial time. The upshot of this result is it's a new application of quantum computers, right? So we can use quantum computers to solve this balls and springs problem, and also more generally simulating a classical system of coupled harmonic oscillators. And in fact, it's a new application with an exponential speedup. And why is it an exponential speedup? And that's because of the third bullet point. That is, we show that this problem is BQP complete. And what that means is it's among the hardest problems that a quantum computer can solve efficiently, or more technically, what it means is that any problem that can be solved by a quantum computer in polynomial time can be reduced to this problem efficiently by a classical polynomial time algorithm. So the upshot of this result, other than proving that this is an exponential speedup, is that we can design new quantum algorithms using this problem. So in principle, you could design a completely new quantum algorithm just by reasoning about classical balls and springs. So for many of us, maybe we have more intuition about quantum computing and quantum algorithms, so maybe it's not that useful, but I'm sure there's people out there who think that Newtonian physics is far more intuitive, and maybe they would like this way of designing quantum algorithms. And finally, as a bonus, we give another kind of a piece of evidence showing that this problem is hard. We show a exponential separation in the quantum query model. And in this talk, because I only have 20 minutes, I'll spend most of my time explaining what the problem is. Hopefully that should become clear to everyone. I've pitched this talk at a general audience level, so hopefully everyone should be able to understand what the problem is. I'll say a little bit about how we solve the problem and give you some intuition for what the algorithm looks like. And I'll give you some intuition for why the problem is hard. I won't get into real technical details about any of these things, so hopefully the talk should be easy to follow for everyone, regardless of your background. All right, so let's start with a description of the problem. So it starts out with this very general time evolution problem in physics. And you've probably seen this problem before in some form of the other. I remember I had to solve many high school problems that looked exactly like this. And the format is always the same. You're given the description of a physical system. So what that means is you're told how the system evolves with time. You're told what the system is doing right now, which means you're given its initial state. And you're given some time t, and you're asked, what will the system look like after time t? And just as a concrete example, let's say we're talking about a system from Newtonian mechanics, so just classical physics. What would be the state of the system? So in Newtonian physics, the state of the system is just the positions and velocities of all of your particles. And then you have to tell me, how does the system evolve with time? Like what equations of motion does the system follow? That would be, you have to tell me Newton's law, F equals ma. To specify that equation, you have to tell me the left-hand side and the right-hand side. The left-hand side is all the forces that act on all the particles. The right-hand side is just the masses of all the particles. And once you've told me all of this stuff, I can tell you what the system will look like after some time t. Right? So we can define a computational problem from this, which is just the input is the forces, the masses, the initial positions, velocities, time t, and the output is the position and velocities at time t. Okay, cool. That's pretty straightforward. And this is just like the general setup. And now let me specialize it to this balls and springs problem. So I want to consider a system with a bunch of balls, let's say capital N balls. And between any pair of balls, I'm going to allow potentially a spring. So this is just one example of, 8 balls connected by springs. And I'm also going to allow walls. So balls can also be connected to walls by springs. Like in this picture, there's two walls, one on the left, one on the right. And I need to tell you how the system evolves with time. So we need to understand the physics of springs, essentially. Fortunately, that's really easy. To the force that a spring applies, at least like in idealized springs, a spring is given by Hooke's law, and it says that the force is proportional to, or in fact, it's equal to minus kappa times delta x. Kappa is the spring constant. It measures how powerful is the spring. So if kappa is 0, that means the spring doesn't do anything at all. If kappa is very large, that means the spring is very strong. And what that means is if you compress it by some amount, it pushes out strongly, and if you stretch it, it'll pull inwards. And the way springs work is, or at least ideal springs work, is that the force exerted by the spring is proportional to the amount by which you compressed it or stretched it. So that's the force equation. There's a minus sign kind of to remind you that if you compress a spring, it pushes outwards, and if you stretch a spring, it pulls inwards. Okay, so now we understand the physics of springs. That's all we need to know. And so now we can formalize a proper computational problem about balls and springs. And so here's a first attempt. It essentially just takes the problem I was talking about 2 slides ago and formats it as a computational problem. So what are your inputs? So the inputs are all the masses. There's n balls. You have to tell me all of their masses, and these are m1 through mn. You have to tell me the value of all of these spring constants. So as I said, any pair of balls can be connected by a spring. So there's n balls, so there can be n choose 2 springs. So that's the first n choose 2 spring constants that you have to tell me. And each of the balls I also optionally allow you to connect it to a wall, so that's another n spring constants. I'm going to arrange these in a matrix, and I'll call it kappa. So kappa ij, which is the same as kappa ji, is the spring constant of the spring that connects ball I to ball j, and kappa ii would be the spring constant of the spring that connects the ball to the wall. Okay, good. So that's masses and spring constants. I have to tell you all the initial positions and velocities. I'm going to call these xi of 0. So the argument is the time. So the initial time is t equals 0. So each ball's initial position is xi of 0, and the velocity is xi dot of 0. So throughout this talk, I'm going to denote velocities with as xi dot. Dot is for time derivative. Okay. And just to be clear, following standard physics convention, all of the positions are measured relative to the rest position of the balls. So for example, in the picture down below, if all the balls are at rest, they're at stable equilibrium, nobody's moving around, everybody's happy, that would be considered rest position, and so that would be considered all of them having position coordinate equal to 0. And finally, the last input is time, of course, and the output would be the final positions and velocities at this time t, okay, which I'm going to call xi of t and xi dot of t. So this is a computational problem, a well-defined computational problem we could study. And let's see, how much time does it take to solve this problem classically? It turns out you can solve this problem in polynomial time, classically. So what I mean is you can solve it in time poly of capital N, the number of balls. And clearly you need something like at least linear time, like linear and n time to solve this, either classically or quantumly, it really doesn't matter, because the output is of size n, right? So either a classical computer or a quantum computer, if it has to write down n numbers as output, it takes n time. So you can't possibly get an exponential speed up on a quantum computer for this problem, right? Because even classical computers solve this problem in polynomial time, and a quantum computer must take at least linear time. So this is not the problem for which we give you an exponential speed up. But this motivates the problem, and we're trying to capture this problem, but we're trying to capture it in a way that an exponential speed up is actually possible. Okay, so how do we do this? And we use a common trick that you might have seen before in quantum computing, which is we want to represent this problem that's about n balls, but we want to represent it with an input of size that's exponentially smaller than n, so an input of size log n. So let me tell you about how we do this. I'm going to call this a succinct problem. So because I want to talk about this smaller number, which I'm going to call little n, it's going to be a little confusing. I should have chosen different variable names, but capital N is 2 to the little n. Actually, this is pretty common convention. You might see this in quantum computing textbooks as well. So instead of thinking of there as being capital N balls, think of there as being 2 to the little n balls. And I want to think of this as exponentially many balls. So 2 to the n is a very large number. And I want to describe the problem with polynomial size inputs and outputs. So polynomial in little n. So just to be clear, I want to talk about a system that has 2 to the n balls, but I want to tell you about the system in only poly n size, and I want the output also to be of poly n size. And this will open up the possibility of there being an exponential speedup. So how do I do this? So recall that there were 4 inputs from the previous slide: masses, spring constants, initial positions, velocities, and time. So let's start with the masses. So what I do is, instead of giving you the masses as an explicit list of n numbers, capital N numbers, like m1 through mn, I'm going to give you a little circuit, maybe even a classical circuit of polynomial size. And what this circuit does is it takes in as input the name of a mass. So how many masses are there? There's 2 to the n masses. So the name of a mass, the label of a mass, is only an n-bit string. So that's fine. A polynomial size circuit can take in an n-bit string. And it'll output the value of this of mi. So this kind of representation of this vector of masses is not possible for all vectors. It suggests that there's some kind of structure to these masses. So when is this possible? Just to give you some examples, like if mi is some function of I, like the ith mass is always I squared or something, like that would be an example where there's a polynomial size circuit, or if all the masses are equal, if mi equals to 1 for all I, that would be an example of where there is a polynomial size circuit describing this. So we're going to assume that the masses are given in this way. Then let's get to the spring constants. The spring constant were described by a matrix, as I said before. This K matrix, I'm going to assume it's sparse. And what that means is, even though it's a matrix of size 2 to the n by 2 to the n, there's at most poly n non-zero entries in any row or column. And the way the matrix is described is, again, by a polynomial size circuit, which accepts the label of a row and tells me all of the non-zero entries in that row. Because there's only polynomially many non-zero entries in any row, this can be done by a polynomial size circuit. Those of you who came to my tutorial on Sunday, I also described how Hamiltonians, sparse Hamiltonians, are described, and this was exactly the same representation. So this is a common representation that's used in quantum computing for describing exponentially large objects. So it's not new. Okay, so that's masses and spring constants. The third thing was the initial conditions. I had to tell you all of the positions and velocities of these exponentially many balls. So I don't want to do that. So what I'm going to do is just assume that the system starts out with pretty much the entire system at rest. So pretty much all of the positions are 0, pretty much all the velocities are 0. There's at most polynomially many balls who have non-trivial velocity or non-trivial position. And because I've assumed this, the input is now size poly n, right? You just have to tell me which balls have non-trivial velocity, what's the velocity, which balls have non-zero position, tell me what the position is. So, and the rest are assumed to be 0. So this is not an exponentially large input anymore. The last thing was time. That's okay. That's just t. You just tell me what that number is. And in fact, there's a bunch of numbers on the previous slide and also here that have to be specified, and all of them are going to be assumed to be poly n. Okay, so that's the inputs, and now everything is specified with a polynomial-sized input. So I'm still talking about 2 to the n balls, but my input size is only poly n. Okay, so this is really important. This is how this is going to open up the possibility of an exponential speedup. And finally, let's talk about the output. The output also, the same question arises. You want to specify all of these numbers. There's 2 to the n of them. We can't write them all down. We want to come up with a polynomial-sized description. And unlike the input, you can't just assume that some of them are non-zero, because that's not in your control, right? The output is just what the system is doing at time t. So to make the problem simpler, I'm just going to ask for the velocity of the first ball to some additive error, inverse polynomial in n. So we can actually solve a much more general task, but I'm just going to pick the simplest task to explain what the problem is. And this task will already have all of the properties I claimed earlier, like it's in BQP, it's BQP complete, etc. So now again, the output is not exponential size, right? You don't have to output 2 to the n numbers, you just have to output one number, the velocity of the first ball at time t. Okay, so that's the problem. And what are our results? What we show is that this problem is in BQP, which means there's an efficient polynomial time quantum algorithm for solving this problem. As I said, we actually solve a more general problem. It's a sampling task, but I won't describe it in any detail. The thing that you might worry after this, after seeing this description of the problem, is I took a problem that was reasonably natural, and then I put a whole bunch of constraints on it, right? I said that pretty much everything starts out at rest, and the masses are described by some kind of very compressed circuit. The spring constants are described by a compressed circuit. You might think that I've put so many constraints on the problem that now it becomes easy classically, right? Like, what if the problem is too easy now? Why would it still take time proportional to the number of balls classically? So for that, we proved that the problem is actually BQP hard, or in other words, which implies that it's BQP complete. And as I said before, what this means is that it is among the hardest problems that's solved by a quantum computer efficiently. Or in other words, every problem that can be solved on a quantum computer in polynomial time, like whatever your favorite quantum algorithms, Shor's algorithm, et cetera, can be reduced to this problem. So we do not expect there to be a classical polynomial time algorithm for this. In fact, the problem remains hard even if we add further constraints. So these are just some examples of constraints you can add. Like you can say all the masses are the same, all the spring constants are between 0 and 4, the connectivity is really sparse, every ball is connected to at most 4 other balls, everybody starts out at rest, and only 2 balls have non-zero velocity. Even with all of these extra conditions, the problem still remains hard. It captures the power of quantum computing. And finally, as I said on my summary slide, as a query problem, we can show an exponential speedup. So what's going on in this query problem? So this is just for people who like query complexity and are familiar with the model, because I'm not going to explain in any great detail. In the query model, everything is given to you explicitly. The only thing that has to be queried is this kappa matrix, the spring constant matrix. And what we can show is our algorithm will solve this problem by making only polynomially many queries to this kappa matrix, whereas any classical algorithm will need to make 2 to the omega inquiries or exponentially many queries. So that's an exponential separation in the query complexity model. Okay, good. So that's what we show. Let me tell you a little bit about how our algorithm works. I was going to say why balls and springs. So, okay, those of you who are physicists will probably already know why I'm talking about balls and springs, and those of you who aren't are like, why would I care about this particular system? So it's not really just this particular system. It turns out that the same equations of motion that govern balls and springs govern a whole bunch of other physical systems. Here are some examples, and it's actually not a coincidence. There's a deep reason. It's because if you analyze any physical system close to stable equilibrium, and for broad classes of systems, you will always end up getting the same equations. Technically, it holds for systems that are governed by a conservative force. But anyway, I won't talk more about this, but this comes up all over the place. So that's the short version. This talk isn't just about simulating systems of balls and springs, but it also applies to simulating these 3 examples, but also tons of other examples. Okay. So let me tell you quickly about how our quantum algorithm works. Whenever you see an exponential speedup, you should think about where is the exponential speedup coming from, and our exponential speedup is coming from a reduction to Hamiltonian simulation, or quantum time evolution, which is a known exponential speedup. So we know that this problem can be solved on a quantum computer exponentially fast. And so how do we take our problem and reduce it to this quantum time evolution problem? We map our problem, so our problem is, again, remember, time evolution of capital N balls and springs, to the time evolution of a quantum system, but the quantum system is only going to be on log n qubits. Right, so the numbers check out because specifying the positions and velocities of n balls requires like 2n numbers, and specifying a quantum state on log n qubits also needs like n numbers. Right? So this is theta log n, so I have some freedom here. So I'm going to encode all of these position and velocities into a quantum state. So that's one map. And the second thing is, what we do is we show that the time evolution of the original system, the classical system, can be mapped to time evolution of the quantum system. So from the original system, which was these Newton's laws with these spring constants and all that stuff, how the classical system evolves, we can come up with a quantum Hamiltonian such that if you apply time evolution of the quantum Hamiltonian on the quantum state, you'll get an analogous, the quantum state at time t. This is better explained with a picture. So at the top left is the classical state at time 0, which is positions and velocities at time 0. Let's say we go down first. We map that to a quantum state. Then that quantum state, we evolve with a quantum Hamiltonian that we constructed, and you'll get a quantum state at time t. And this object is the same as if you'd gone the other way, which is you started with your classical state at time 0, you time evolved it with Newton's equations and got a classical state at time t, and then applied the same map that goes from classical states to quantum states and gives you, and you'll get the same object over there. So that's the heart of the speedup, a reduction to quantum time evolution, to quantum Hamiltonian evolution. And if you're wondering, how does this work? I'm not going to get into the technical details. There's some math to show how this Hamiltonian is constructed. I can give you just one little piece of intuition for how we do the state mapping. And so what's going on? What's a quantum state? Just very abstractly, a quantum state is just a vector with fixed L2 norm. Its L2 norm is 1. If you take this classical state, just a vector of positions and velocities, and take its L2 norm, it won't necessarily be 1. That's okay. You can just divide by its L2 norm and make its L2 norm 1. But the problem is its L2 norm will not be conserved during time evolution. So just because your positions and velocities have some L2 norm at time equal to 0, as you evolve this with Newton's equations, this is not going to be conserved. Whereas quantum time dynamics is unitary. The norm of the vector is always conserved. So the map cannot be something straightforward like, oh, just take all the positions and velocities and stack them into a long vector, and that's your quantum state. Divide by something to make its norm 1. That's okay. But that cannot be your map. It has to go to some object whose norm remains conserved throughout the computation. And what we do is use the fact that energy is conserved in the system. So the vector that we map to actually encodes the kinetic and potential energies of all the constituents of our system. And that object's norm will be conserved because the norm is the energy. And that's some intuition for why this works. Okay, so that's the algorithm. And maybe let me tell you a little bit about the lower bound for why this problem is hard. And this relies on this problem called the glued trees problem. Maybe some of you have seen this before. It's a famous problem in query complexity. So what's going on over here is you're given this graph, which looks like one complete balanced binary tree on the left, one complete balanced binary tree on the right, and some kind of random cycle in the middle that connects them. And you're given the label of the entrance vertex, and you don't actually have access to the graph. You have query access to the graph locally. And what that means is you can submit to some black box the name of any vertex, and the black box will tell you what its neighbors are. So you start out by only knowing the name of the entrance vertex. So the only query you can make to the black box that's meaningful is ask it the entrance vertex, this neighborhood, and it'll say, you know, this vertex and that vertex are connected to the entrance. And only with this kind of black box access, your job is to find the label of the exit vertex. And it's already known that this problem is super hard. Classically, it takes exponentially many queries. Exponential in little n, which is the depth of this tree. So there's 2 to the n roughly exponential vertices on this graph, but the depth of this graph is only n, or 2n, that we have labeled it. Right, so how do you solve this problem? This problem is super hard classically. We want to solve this using balls and springs. So just, if you stare at this graph, where would you think of putting balls and where would you want to put springs? Right? I think there's only one obvious way to do it, which is you put balls at where all the vertices are and you put springs where the edges are, because you know the vertices kind of look like balls. And that's what we do. And in fact, you put a ball just of mass 1, so the masses are all equal. At every vertex, you put a spring constant 1 at every edge. And what do? You start out with all of the masses at rest, and just the first mass, the entrance, the one you know, you give that some velocity. We'll just say velocity 1. And what we can prove is after some polynomial time, the exit vertex will have some inverse polynomial velocity, so some detectable velocity. And then you'll be able to solve it with our problem. And therefore, you can solve the glued trees problem using our algorithm. And the classic lower bound already exists from the original problem that introduced this problem, so that gives you an exponential quantum classical separation for this glued trees problem. Okay, cool. So maybe that's all I wanted to say. I'm out of time. I'll just put up this slide of summary and open questions if anybody wants to ask me any more, but let me end my talk there. Thank you so much.
Thanks, Robin, for the nice talk. Are there any questions?
Hi, nice talk, thanks. Can you talk about the energy in the system? I understand that the velocity can only be in a polynomial number of balls, but there are an exponential number of balls. So the total energy of the system is either like not extensive, or some of the balls have to have exponential velocity.
Okay, so this is about glued trees, right? Yeah, good question. So let's take this example. So here what's happening is I'm starting out with all the balls having mass 1, and only one ball has any velocity. That's the first one. So the total energy of the system is just half mv squared. So as the system evolves in time, the total energy is going to remain half, because conservation of energy. And here, for example, all I'm claiming is even though there's 2 to the n balls, what ends up happening is if you evolve for polynomial time, the energy actually gets roughly equally distributed between all the columns. There's only 2n columns, and what ends up happening is each column has roughly the same amount of energy, which is 1 over 2n. And so the exit column, which has only one ball in it, gets energy roughly 1 over 2n. So that's why it's a detectable amount of energy. If it was an exponentially small amount of energy, we wouldn't be able to detect it. But it turns out it's in fact inverse polynomial, and that's why the algorithm works.
Okay.
Could you get some intuition as to how you would map other classical problems to this problem, or in general to Hamiltonian simulation?
Oof, yeah, that's a tough one. Right, let's take that separately. So how would you map other classical systems to this one? As I said, this system itself, this classical coupled harmonic oscillator, comes up like all over the place. So maybe the problem you're interested in is already modeled by this, as many problems are. If not, I don't really have any great intuition for when you can take an existing problem and map it to a system of coupled harmonic oscillators. but presumably a lot of people do. Like, I get the impression that I'm not a physicist, but that this problem is very well studied in physics, and people have all kinds of ways of how this problem pops up everywhere. So I expect there's some understanding of how to do this, but I don't have any great answers. Your second question, how would you map a classical problem to Hamiltonian simulation? This is generally pretty hard. I was actually surprised that this even worked for this work, because it's kind of going the wrong way, right? You generally want to take a quantum problem and map it to a classical system and solve that, because we want to solve quantum problems on classical computers. This is weird. This is like the direction that nobody would want to do, which is that you take a classical problem and map it to a quantum system and do quantum time evolution, because quantum time evolution is really hard on classical computers. So the fact that this exists even is kind of unexpected. I wouldn't have thought expected. So I certainly have no advice on how you take general classical problems and map them to quantum time evolution.
I see. Is it related to partial differential equations?
Is it related to partial differential equations? I don't know. Yeah, what do you mean? Yeah.
Well, because the Schrodinger equation is like a differential equation.
Oh, I see, in that sense. Yeah, I mean, the two equations, so the equation that comes up for balls and springs, this coupled classical harmonic oscillators, it's a second order equation, and it looks like, yeah, I don't have the equation here, but it looks like something like some vector second time derivative equals minus some PSD matrix times the original vector. Whereas the Schrodinger equation is a first order equation that looks like, okay, maybe everybody knows what the Schrodinger equation is. So if you just look at these two equations, it's not clear that you can map one to the other. We do have a proof. So actually, we have two ways of deriving this algorithm. I only talked about one. There's a second way we have of deriving this algorithm, which is very syntactic. It starts out with a second order differential equation, and it does some math. It adds and subtracts some terms or whatever, and arrives at the Schrodinger equation. So that would be a very syntactic way to view it, and maybe that would answer your question of like, is it coming from the nature of the differential equation? And if you go through that proof, it kind of is. Yeah, it's because the equation looks like that. The proof I talked about with these energies and stuff, that's a second proof that we get in our paper.
Thank you.
And the last question, I think there's one up there.
Hi.
Yeah, you said that the number of constants for the springs was logarithmic, like small n. But doesn't it make the graph disconnected?
Good question. So it's not that the number of constants for the springs is like little n, which is log of the total number of masses or springs. It's that I'm describing it by a small, which is like little n or log capital N sized classical circuit. So this is something we do all the time. We often even describe exponentially large Hamiltonians by classical circuits of polynomial size. And it doesn't mean that there's only polynomially many spring constants, because that would, of course, mean that the graph is disconnected. It just means that there's some very ordered way of describing what all of the exponentially many spring constants or masses are.
Yeah, thanks.
And I know there are more questions, but we're running short on time, so hopefully you can ask them to Robin during the break. Let's thank our speakers from this session again, and enjoy the lunch.